Okay, section 13.2 has to do with saturated, unsaturated, and supersaturated solutions. Remember, solubility refers to whether something can dissolve in a solvent and how much. Most solutes you can't just add an infinite amount to the solution. For example, if I have 1 cup of water and I put a tablespoon of salt in there, then that will dissolve. Honestly, a tablespoon is probably getting to the point where it would take a long time and some vigorous stirring. If I put 3 or 4 tablespoons of salt into my cup of water, that's probably going to be to the point where it won't dissolve all of that. It's not a matter of time and stirring. I could stir it vigorously for 10,000 years and it will just never dissolve. That means that the solution has reached the limit of its solubility. So solubility is often given in units of grams per grams, and this is actually, let me be a little bit more clear. This is grams of solute in grams of solution. So if I have 100 grams of solution, then the solubility would tell me how many grams of solute I can put in that 100 grams of solution. And in fact, it's often expressed not just in grams per 1 gram, but grams per 100 grams of solution. This will make more sense when I show you a chart in a little bit. But the solubility is going to tell you how much solute you can put into solution before it stops. And why would it stop? Well, we can think of the solvation of sodium chloride. We're not going to write water as a reactant here because it's not actually reacting. It's not forming or breaking any bonds. But it is the environment in which the sodium chloride can form an aqueous solution. Okay, so sodium chloride solid goes to sodium chloride aqueous. Well, this is actually an equilibrium. There we are. And so the reason you can only dissolve so much salt before it stops dissolving is because it will eventually reach equilibrium. And once you reach equilibrium, you may recall that solids do not appear in the equilibrium expression. And so adding more solid is not going to perturb the equilibrium at all. Le Chatelier's principle will not apply to sodium chloride. You can add solid all day long and it's not going to drive the reaction anywhere. And so once you reach equilibrium, then you cannot add any more sodium chloride to the solution. Now, thinking of solvation in terms of an equilibrium like this also helps us to understand how the solubility might respond to temperature. So you may have some kind of vague intuition that if you want to dissolve more sugar in water or more salt in water, you can do so by putting it on the stove and heating up the water. And that is because this process is an endothermic process. So for sodium chloride, for sugar, and for many other solutes, the solvation process is actually endothermic. It's only slightly endothermic. If it were too endothermic, then the compound would be insoluble altogether. But if it's just slightly endothermic, then we can write heat here as if it is a reactant. And Le Chatelier's principle tells us that if we increase the temperature, then that will drive toward products. So solubility is actually a function of temperature. The higher temperature your water is, the more sodium chloride you can dissolve in it. Now some solutes are going to be exothermic in their enthalpy of solution, And so it would have the reverse effect. If you increase the temperature, then the solubility would actually go down. And let's think about a particular case here. If I have something like if I'm dissolving a gas into a liquid, like say nitrogen dissolving into water, well, these gas particles are almost never in contact with each other. Remember, gases are composed of empty space, and encounters between particles are brief and rare. And so there's almost no attractive forces going on in the gaseous state. But here the nitrogen is surrounded by solvent molecules, and so there are always going to be an increase in attractive forces for a gas dissolving in a liquid. And that means they will always be exothermic. And so gases will always be more soluble at low temperatures. Let me draw it this way. Let's always talk in terms of higher solubility. So at a lower temperature, Le Chatelier's principle would drive the solvation of a gas to toward products. And so if we think about ocean water, I remember as a kid assuming that tropical ocean waters is where all of the life is at, and that they're the waters that are more healthy for fish. And it's always kind of surprising, how is it that any fish live in Arctic waters at all? It's freezing cold, and it seems very much like it's not amenable to life. But the reality is that Arctic waters are abundant with fish. And the reason is because the colder water is going to have more oxygen dissolved in it. And in many ways, oxygen is kind of the limiting factor here. So Arctic waters are a better environment for many fish than tropical waters, because what they need is oxygen. Okay, so let's look at table 13.4. There we go. And this shows the solubility versus temperature for some solid solutes in water. And you'll notice it's in grams per 100 grams. And so some things are pretty modestly soluble. Like here we have KNO3 and SO2 at the bottom end of about 20 grams per 100 grams at around the freezing point of water. Then you have some things like table sugar, which has an abundance of OH groups that are able to hydrogen bond with the water, and its solubility is enormous. 180 grams of sugar for every 100 grams of water. And as the temperature increases, table sugar's solubility only goes up. Has anyone ever made candy, like caramel or toffee? You do that by dissolving what seems like an absurd amount of sugar into the water. But as you heat it up, it dissolves. And then you add even more sugar. And you heat it up and it dissolves, and you add even more sugar. And anyway, it's, to me at least, it's actually a really remarkable process, just how much sugar you can squeeze into the water, especially as you raise the temperature. And by the end, the sugar water solution has an extremely high temperature because it's able to go above the boiling point with more and more sugar being added to it. And that's a phenomenon we'll actually discuss in 2 days from now when we talk about colligative properties. So things like table sugar, their solubility goes up with increased temperatures. So we know that their enthalpy of solution is positive. They're endothermic. KNO3 is as well. Something like NaCl, you'll notice it is positively sloped, but only modestly so. And so NaCl has an enthalpy of solution that's very small, but positive. And then NH3 and SO2, these are two examples of gases At room temperature, both of these are gases, and you'll notice their solubility goes down as the temperature increases. You can find some examples of solids that would do that as well, but gases are the notable exceptions here. Okay, so we can take advantage of solubility to do all sorts of clever things. So one process is recrystallization. And when you do organic chemistry lab, you'll go through this process frequently. Recrystallization is a way to purify the product of a chemical reaction. So suppose you're doing an organic reaction and you want to generate a particular product. All the time in organic chemistry, you're going to face incomplete reaction, side reactions. You'll intentionally have one of the reagents in excess. And so even a very good successful reaction is going to have a product that is adulterated with all sorts of other things that you want to purify away. Well, recrystallization is a good way to do that. You'll take advantage of the fact that the solubility curve is probably looking something like this. And you'll pick a solvent that is going to dissolve all of your impurities, but your product is not very soluble in your solvent. And then you'll put the solvent in there and increase the temperature until everything dissolves, including your product. Once everything is dissolved, then you'll take that solution and put it on ice. And when you cool it down, the solubility of everything is going to drop, but you've chosen your solvent carefully so that all of your impurities will still remain in solution. Their solubility, even at the low temperature, is high enough that they remain in solution, but your desired product will, at low temperatures, have a solubility low enough that it will recrystallize. That is, it'll come out of solution and form crystals. Anyway, so this is a process that you'll do frequently. You dissolve the solute and your impurities in a hot solvent with a minimum volume, as little solvent as you can manage. And you heat it up, and then once everything's dissolved, you cool down the solvent. This reduces the solubility, and your product will recrystallize out. And then you can just wash away the solvent, and it will wash away all the impurities that are dissolved in it, leaving behind your nice purified crystal of your product. Okay, now we need to talk about three different words here. Unsaturated, saturated, and supersaturated. So these are three different ways to describe the state of the solubility equilibrium. An unsaturated solution is one that could still take more solvent. It hasn't reached the saturation point yet. And if we think about the equilibrium right here, an unsaturated solution is one in which Q is less than K. Or in other words, the reaction quotient is smaller than the equilibrium constant. Now, usually when you have an equilibrium reaction that's not at equilibrium, then it will shift in order to reach equilibrium. But in solvation reactions, your reactant is a solid. It doesn't show up in the equilibrium expression. And once you run out of solid, once you've dissolved all of the sample that you have, then there's no way for the system to shift in order to reach equilibrium. So an unsaturated solution will never really reach equilibrium here unless you continue to add more solid. A saturated solution is where you are exactly at that equilibrium point, where Q is precisely equal to K. And when you phrase it that way, it makes it sound like you have to add just the right amount of solute. But in reality, all you need to do is add at least enough solid solute to saturate it, and then you'll be saturated. And if you add more solid, then because of the way equilibrium works with solid reactants, then you'll reach saturation and just stay there. So if I see a beaker and it's just filled with water, I'm going to assume that this solution is not saturated. I suppose it's possible that someone added exactly precisely enough solid to saturate it, but it's very unlikely. If I want to have a saturated solution, then you add enough solid so that after you've stirred it for a long time and everything is dissolved, you still have some solid left over sitting at the bottom of the beaker. That's how you really know that you've reached a saturated solution. And what about a supersaturated solution? A supersaturated solution is one where the concentration of your solute is greater than the solubility. And in other words, Q is greater than K. And it's a bit of an unnatural state, so you need to be clever to create a supersaturated solution. We've already talked about one way we can do that. In the quiz, which I recorded before this, we talk about one way to create a supersaturated solution, and that is by changing the conditions. So let's go back to our temperature dependence of solubility. If I take some water and I put, let's say I put 240 grams of table sugar in it, I'm going to have to heat it up to, about 40 or 50 degrees Celsius in order to dissolve that much table sugar. And I can do that easily on the stove. But what if I then take my solution off of the stove and I let it cool back down to room temperature, where the solubility is only about 200 grams of sugar per 100 grams of water? Well, then I'll have a situation where I have dissolved more sugar into the solution than the solubility states. And so that is a supersaturated solution. You can get a supersaturated solution by heating up the solvent, dissolving to the saturation limit at that higher temperature, and then cooling it down slowly and carefully. And sometimes a supersaturated solution, as it cools down, it will sort of immediately recrystallize. And so the value of Q sort of follows K as the temperature cools down. But if you're careful and make sure that you have no impurities and you have glassware that is nice and clean and smooth, then you can actually cool down the solution carefully, and the dissolved solute is never able to recrystallize. It sort of requires a catalyst, a seed crystal or some sort of a nucleation site to start that process. And so even though it's not at equilibrium, it's not technically in thermodynamic equilibrium, it can be metastable and remain in a supersaturated state for a long time. And your textbook actually has a good video of a demonstration of recrystallizing from a supersaturated solution. So I'll encourage you to watch that video in your textbook. So supersaturated solutions are carefully constructed, taking advantage of the change of solubility under different conditions. Now, you can talk about the solubility of solids in terms of that grams of solute per 100 grams of solution. But for gases, it actually is a little bit different. In fact, in that table that we showed, there's a little bit of missing information, and that is what is the pressure of the gas above the solution. So, for example, one sec. I'm going to jump ahead a little bit to figure 13.10, which is talking about something we'll talk about in a couple of sections. But just looking at the figure on the left here, a volatile solvent, let's pretend instead that this is a solvent and gas particles that are dissolving into the solution. Well, what we have at saturation is an equilibrium between the gas particles that are falling down into solution and getting stuck, and the solute particles that are in solution that are able to escape into the gas phase. Oops, I'm having trouble drawing. There we go. Oh my goodness. Okay, so there's going to be an equilibrium between these two processes, right? And the frequency of collisions between the gas phase and the solvent are going to depend on the pressure of the gas above the solution. Anyway, what this all kind of amounts to is that the molar concentration of a gas in solution is going to be proportional to the partial pressure of that gas. If I have a higher pressure of gas, then I'll actually increase the solubility of that gas in solution, even if the temperature remains constant. This is called Henry's law. And Henry's law basically says that the concentration of the gas is equal to some, oops, that's a lowercase k, some constant, which we call the Henry's law constant. And each gas is going to have its own Henry's law constant. Actually, each combination of gas and solvent. So oxygen would have a Henry's law constant in water. And nitrogen would have a different Henry's law constant in water. And oxygen would have a different Henry's law constant in acetone, for example. Okay, so there's the Henry's law constant times the partial pressure of that gas above the water. So let's use Henry's law here and do a little bit of problem solving. So the Henry's law constant for carbon dioxide is equal to 0.034 molar per atmosphere. Okay, that's barely in screen, sorry. And in the factory, when cans of soft drink are being manufactured, they are pressurized to a pressure of about 2.5 atmospheres. So the pressure of carbon dioxide is equal to 2.5 atmospheres in the factory where cans of, say, Coca-Cola are being sealed and before they're sent out to the store. So what is the molar concentration of carbon dioxide in a can of soft drink from the store? Well, we'll take that Henry's law constant, 0.034 molar per atmosphere. and we'll multiply it by that 2.5 atmospheres of partial pressure. Okay, so let's see what that works out to be. We have 0.034 times 2.5. Looks like the molar concentration is going to be 0.085 equals 0.085 molar. So that is Henry's law. Okay, we've got two more words that we need to learn. There's kind of a lot of vocabulary. Saturated, unsaturated, supersaturated. Here we have two more words. Miscible and immiscible. Miscible is a special word for two liquids that can dissolve in any ratio. And so that means that they kind of have an infinite solubility in each other. So if I start with 100 grams of water and then I add some ethanol, well, water and ethanol are miscible. So I can add 10 grams of ethanol and they dissolve. I can add 100 grams of ethanol and they dissolve. I can add 400 grams of ethanol and they'll dissolve. And what really happens is somewhere in the middle there, it sort of transitions where it started with water as the solvent and ethanol as the solute. Well, eventually I'll have added so much ethanol that now ethanol is the solvent and water is the solute. Nothing special happens at that transition. It's just, you can mix them in any ratio at all. I could have a little bit of water and a lot of ethanol and it would dissolve fine. I could have a little bit of ethanol and a lot of water and that would mix fine, and everywhere in between. So those are miscible liquids. Immiscible liquids are ones that are not soluble together at all. So something like oil and water. They don't mix together at all, not in any ratio at all. So they are immiscible. Of course, there's a middle ground, doesn't have a good name, of liquids that are somewhat soluble in each other, but not infinitely so. There's no good name for those, but we've got these special words to describe liquids that are infinitely soluble in each other and completely insoluble with each other, miscible and immiscible. Okay, that's it for 13.2.